All right. Welcome everyone. You're really welcome to this class. This is the very first class on random variables in statistics. It's quite a very interesting topic, and I really will persuade you to. All right. Am I still audible? All right. Am I still audible? Can you hear me, please? Can you hear me, please? Can you confirm if I'm audible? Let me be sure the network is not disturbed. Okay. Can you hear me? Is it clear? Good evening, everyone. Okay. All right. Okay, that's great. It's great to know that you can hear me. So, as I was saying, we are going to pick up from our understanding on probability. Random variable is quite one of the basic knowledge you need to understand when dealing with probability distribution, because we would always be using the term a random variable X. And I really want you to have the right understanding. And that's why we're going to be introducing random variables in tonight's class. Now, what do we define random variable as? Just for you to understand it with words, a random variable is a numerical value assigned to the outcome of a random process or experiment. Now, you guys know already that I'm not very interested in so much of English. I love to always break things down mathematically. Now, we say a random variable is a numerical value. Just for context sake, a random variable, we would often use the short for random variable as RV. It's a numerical value assigned to the outcome of a random process. Or experiment. All right. Now, if you see clearly, of course, I believe we have dealt with experiment while we were talking about probability. Now, when performing an experiment, for instance, let's say the tossing of a coin or the tossing of a dice. Now, let's use, for instance, the tossing of a dice. You have we have just 6 different possible outcomes. We say 1, 2, 3, 4, 5, 6. And when seeing a coin, we have 2 possible outcomes. For a coin, we have head or tail. Now, these are some of the things we did when we're dealing with probability. Now, these are not all the examples on random experiment. We have several random experiments, which, of course, we have done so much of it when we're dealing with probability. Now, when dealing with random experiments, the word random there means, of course, there is everything is by chance. So we don't have a predefined outcome when we're dealing with a random experiment. Once there is a predefined outcome, we're no longer dealing with a random experiment. And every probability will always have to do with random experiment. So when we say random variable, the random there is standing for the fact that we're dealing with a random experiment, all right? And the variable, we say random, then we say variable. So random here is because we're dealing with random experiment. Variable, the word variable, we believe we have done this before. It has to do with varying numbers. The word varying numbers. Variable comes from varying numbers. So for instance, when we talk about constant in mathematics, we say constant K, we say constant C. Those constants don't vary. So for instance, let's say we have a constant number 2 in an expression. That constant number 2 will always be 2 everywhere. All right? So if you take that expression to a different function, it will still be the constant 2. All right? But when dealing with variables, variables vary. They are like placeholders. And that's why we always say a variable x. So a variable x could be 1 in a particular expression. It could be 2 in another expression. It could be 2.5 in a different expression. That's the use of the word variables. Variables has to do with varying numbers. So when we say a random variable, that means you're talking about a variable that we use when dealing with random processes or random experiment. All right. Now, we went on to say a random variable is a numerical value assigned to the outcome of a random process. Now, let me run quickly to just a very important keynote that will help you to really understand what we're talking about. Now, let's say, for instance, we're dealing with the tossing of a coin. Before, we used to say the probability of getting a head. Let me write that for you because we did this a lot. Probability of getting a head, you will say the answer was 1/2 or 0.5. This was what we all are very familiar with in our previous topic. But this is a random variable will make you write this in a different way. Let me explain that to you. We're going to be assigning a numerical value to the outcome of a random process. Now, head is the outcome, one of the outcome of this random process of tossing a coin. Of course, tail is also an outcome. Random variable is a numerical value assigned to the outcome, keyword there, outcome, of a random process. Now, we often and always denote random variable with capital letter X or Y. Note that. So when you are dealing with random variables, you'll be seeing a random variable, capital letter X. In some cases, capital letter Y. Now, let me try to rewrite this using the concept of random variable. We can decide to assign this random process of tossing a coin a numerical value of 1 for head and a numerical value of 0 for tail. This means that when dealing with the tossing of a coin, instead of writing probability of head equals to 1/2, we could go on to write probability of now a random variable x being equals to 1 to be equals to 1/2. Of course, conversely, we could write probability of a random variable x being equals to 0 is equals to 1/2. This is a good introduction to the word random variable. Now, I need you to understand that this is a very simple random process containing just 2 outcomes. So you understand that random process, so we're not always going to be having just 2 different outcomes. We could have different possible outcomes depending on the random process we are dealing with. Can you guys indicate if you really understand what I said so far? Can I get feedbacks from the chat box? Do you truly understand what I just said on random variables? Okay. All right. All right. Okay. Okay, some people are talking, some people said yes, some people said I should recap. I'm going to recap because this is the very first class. And let me use another instance that will probably give better understanding. Let's deal with tossing of two coin. I'm sure everybody in this class understand that in tossing of two coin, the sample space is obviously going to be head, head, tail, head, and tail, tail. All right. Now, run this using random variables. Of course, we can define this on the basis of, let's talk about the outcome. So let's say we have the outcome and number of heads. So we have tail, tail, we have tail, head, we have head, tail, we have head, head. The number of heads here is 0, 1, 1, and 2. All right. Now, if we were dealing with just the raw probability, we were going to say the probability of tail tail was something, probability of head tail was something, probability of at least one head. You guys are very familiar with all those stuffs. We did it some few moments back. Now, if we wanted to write this on the basis of random variables, I told you that random variable is a numerical value that will be assigned to the outcome of a random process or a random experiment. Now, instead of writing probability of head head or probability of tail tail, one way you could write your random variables, for instance, let me say one thing. We said our random variable is defined using X or Y. I could decide for an experiment to define my random variable X as the number of heads when tossing two coin. Hear that one more time. I could say my random variable X represents the number of heads when tossing of two coin. Now, random variables are always defined depending on whatever experiment you are dealing with. So if I say my random variable X is being defined as the number of heads when I toss coin, good. This means that look at the outcome when you're tossing two coins. These are the different possibilities. Of course, you can obviously see that these are the resulting number of heads. Instead of writing your probability as this, we are still going to go deeper into the concept of random variable. Obviously, this is just the introductory part. So instead of writing, now I've defined my hex as the number of heads. Remember the number of heads, emphasis, number of heads when tossing two coin. Instead of writing probability of HH, I could go on to write probability of X, random variable X, that's number of heads, don't forget, equals to 0. Of course, this will be this is instead of writing probability of tail tail, all right? Or I could go on to write probability of X equals to 1. This will be a situation when I'm dealing with just one head, obviously. Don't forget, I defined my random variable X as the number of heads. If I define it differently, it will also be showing forth in what I'll be writing. So the whole concept of random variable is just a numerical value. A numerical value. A numerical value. Can you see the numerical value? 0 in this case, 1 in this case. Of course, it can go on and on. A numerical value could be 5, it could be 6, it could be anything. All right? Now, it's a numerical value you assign to the outcome of a random process. Is it much clearer? Is it much clearer? So I could assign 1 to me seeing a head and 0 to me seeing a tail. Now, in the case of when you toss a die, of course, you could have your random variable x representing a set of 1, 2, 3 up till 6. All right. So I can say if my random variable x now, random variable x as the values I see when I toss a dice, that means I could say probability of x is equals to 3. All right. That's a possibility. And probability of x equals to 4, and so on and so forth. So now, this is just the introductory part so that you will be able to understand when we are writing all these things. That it's not, you don't need to see it as an abstract thing. It's just us assigning a numerical value for a process, a random process, for the outcome of a random process. All right. So once you see something being written like this, one of the first things that should come to your mind is, what does this x, random variable x, represent? That should be clearly defined. Oh, it represents this. Oh, it represents that. Your x will always be defined. When you go on and on, when we get into probability distribution functions, you will see how we're going to be defining different random variable x. In some instances, it could be, for instance, that x represents the number of children in a family. X could represent the number of lawyers in a country, right? So what x could be defined will be defined based on outcomes of a random process. Now, don't forget that it must be a random process, because if it's not a random process, that will not be a random variable. All right. Now, I believe you understand this greatly now. Is there anybody still having any issue with understanding what random variable really represents? Anybody still having any issue? All right. Now, I want to go on now to tell you a little bit about why do we, some of you may be wondering that if I could write probability of tail, why then do I go on to write probability of x equals to 0? Why then do I go to write probability of x equals to 1 if I could just write probability of 1 head? Now, one main reason why we use random variables is that they make complex qualitative. This is qualitative. Now, when you talk of qualitative, the opposite is quantitative. They make complex qualitative scenarios manageable. So instead of we saying probability of getting 2 heads equals to 0.25, we can easily just write probability of x equals to 2. All right, equals to 0.25, probability of getting 2 heads. So this is better manageable in mathematics than we writing probability of. So they transform your complex qualitative scenarios to a much more quantitative, manageable thing that you can easily solve mathematically. Now, I also want you to understand that one important use is also that is the fact that they give us the possibility of using, of course, whenever we get an answer like this, we're able to find the expected value. Now, we'll be getting into that, not obviously in this class, but in some other classes, where we can easily get the expected value of, for instance, expected value of a random variable x. You could get it. You could get also the variance of your random variable x. So that's all of it. Allows us to be able to use tools like expected value and variance to analyze the risk and outcomes of random processes. So these are the main reason why we decide while the concept of random variable became very important in statistics. So this is my random variables. I want you to really make sure that the whole concept, especially the introductory part, is much understood before we get into the other subject. Now, let's go into a very, very vital aspect of random variables. We just talked on the definitions. But I want you to understand that if you can deal with different possibilities in your mind, you will see that this will give this will produce two different distinct types of random variables. Because if you take an instance, if I say the precise height of a randomly chosen person, when you look at that, if I talk about, let's say for your class, for instance, if I say the height of people in your class, let's assume we are dealing with a random process that has to do with choosing the precise height of let me just take, for instance, probability of, just for you to understand less ambiguously, probability of, let's say, the height of a student being 2.35 meters. What's probability of getting the height of a student as 2.35 meters? Of course, if we're going to run this experiment in your class, we would have to know the total number of all the height of people we have in the class. And then we then go on to find probability that of getting a 2.35 meter. Now, if you look at this instance now, we're dealing with a more measured data set. This is different from if we're trying to pick a more countable data set. This gives room to a very important distinction in under random variables. And that's the fact that we have what we call discrete random variable, and we have what we call continuous random variable. The reason is because under the term discrete, we'll deal with countable data sets. And under the aspect of continuous, we'll be dealing with measured data sets. Now, this has given birth to probably another controversial aspect of random variables. I'm sure you guys understood the introductory part, but some of you are still trying to grasp your mind around what does discrete means, what does continuous means. Of course, when doing random variables, you need to understand that there are two different types of random variables. Of course, we have discrete random variable, we have continuous random variable. The use of the word discrete there and continuous there, let me delve a little bit into that. When you hear the word discrete data are counted in whole numbers. And I'm sure you can give me a ton of examples of discrete data sets. For instance, your age. Your age is a discrete data, all right? The number of people in your class, the number of male genders in your class, the number of cars in the parking lot, the number of just the number of tables in your class, whatever data set is countable, once you can count it, we call it discrete data. But you see, when we continuous data are measured and can take any value within a range, including decimals. All right? Now, discrete data represents specific distinct points. One, discrete data, 1, 2, 3, specific distinct point. Whereas continuous data represents measurement over a continuous interval or time. All right? 2.38, 5.76 meter, and so on and so forth. All right? Now, I would love you in the chat box to give me some examples of data set that you feel represents discrete. All right? And also give me some that you feel represent continuous. So I'm waiting to see your examples. I want you to really understand the concept of discrete data and continuous data points, so that when we get into the concept of it under random variables, you will be able to really understand it. So can you give me examples of data that would be representing discrete data. I gave you some examples already. Number of students in a class, number of cars in a parking lot, the outcome, a dice, rolling a dice. When you roll a dice, you'll be getting obviously 1, 2, 3, 4, 5, 6. Countable. Number dice rolls. You could roll a dice 3 times, 4 times. You cannot roll a dice 4.5 times. Number of wedding guests, all right? Discrete, somebody wrote discrete height. Height will never be a discrete data because height will be measured. One of the perfect example of a continuous data will be height of students, because your height can be 3.5 meter. Your height can be 7.8. You understand what I'm saying? It doesn't have to necessarily be that you are 7 meter, you are 10 meter, 20 meter. Number of players on a pitch, that's a discrete data, obviously. Right, continuous data, weight of students. Right, that's a continuous data. That's good. Number of Chelsea goals in 5 EPL games. Good. That's a discrete data because it's countable. 5 goals. There's nothing like 5.5 goals. There's nothing like 5.78 goals. Age of students. Discrete data. All right, because we're dealing with a countable data set. So we're talking about 5x, 10x, and so on and so forth. Number of buildings in a compound. All right. Length of a road. Yeah, length of a road. Yeah, exactly. Time. Time will be what? What time will represent? Will time be discrete or continuous? Time will have to be a continuous data point because you don't necessarily have to have 20. You can have 20.25 minutes. You can have 10 points. You understand? And temperature. Temperature will be what? Temperature will be what? Will it be a discrete or a continuous data? Temperature. Temperature has to be continuous, all right? The weight of a dog, continuous, obviously. The speed of a car, what we call that? The speed of a car, continuous, obviously, because somebody can run 15.8 meter per second. It doesn't have to be 15 meter per second, 16 meter per second, 17 meter per second. It doesn't have to go in specific distinct integers like that. It could be 15.8 meter per second. It could be 20.8 meter per second or kilometer per hour, whichever way you measure it. Yeah, so I believe we have done a very sound introduction to discrete and continuous data points. So we can go on now to apply this when dealing with variables. So you just bring the same concept to random variables and it will be so much clearer. So when you're dealing with discrete random variables, let's start from there. And are you still there? So let's run quickly to discrete random variables. All right. Can you guys indicate if you can still hear me? Okay. Now, discrete random variables. I'm going to tell you 2 things that must happen for you to go on to say something is a discrete random variable. Guys, you are at a place where what I want to say next is too important. So make sure you are really here. For you to say something is a discrete random variable, you see these 2 different things I wrote right here? They are key for, I did not say, by the way, let me say this clearly. It is not one or the 2. These 2 things must happen for you to decide that something is a discrete random variable. Now we are already getting into the mathematical aspect of discrete random variable. I've done the introductory part, and I'm sure you guys really understood it. Now, for you to say something is a discrete random variable, these two things must happen, not one or the two. This means the first must be fulfilled. In some cases, the first may be fulfilled, but the second is not fulfilled. In some other cases, maybe otherwise. But for you to say something is a discrete random variable, both must be fulfilled. Now, I want you guys to also note one thing. Now, this thing we wrote here, P of x equals to x. Of course, that was it could also be written as f of x. All right. So I want you to understand nomenclature so you don't get confused. If you see any of the two, you are still saying the same thing. All right. So instead of writing probability of x equals to x here, some people may write it as f of x. In this case, you follow the same pattern, the same thing. All right. Now, for you to, please, can you indicate if you can really hear me, please? I want to be sure that you guys are flowing. Can anybody tell me? I want to get, because I'm seeing some comments that I don't know if it's from your side or it's from here. Is it general or can you really hear me? That's good. Okay. All right. Now, as I was saying, these two things must be fulfilled for you. Let me explain what this means. If the first one, of course, this x here that you're seeing right there represents the values, the numerical values. They could range from what, depending on whatever you're dealing with. For instance, when you're dealing with a Poisson distribution, your x values may start from 1, 2, and so on. When dealing with a Bernoulli will have 0 and 1. When dealing with binomial will have 0 up until n, and so on and so forth. We have different distributions, and your x values will differ depending on your random experiment, depending on whatever you're dealing with. Your x values here will differ. So when you see probability of x equals to this small letter x, understand that this capital letter X represents the random variable. All right. So this small letter x is representing the numerical value we're dealing with. So we're just saying for whatever you're dealing with, it could be x equals to 0, x equals to 1, x equals to anything. That's why we just attach the word small letter x here. You guys need to understand all these things moving forward so that you don't get confused. So x could represent any value, numerical value, but x, this capital letter x here represents the random variable. All right. Wait, I'm not getting positive feedbacks from the chat. Please, is anybody hearing me audibly perfectly? Is anybody hearing me? Okay. So who are the people that are talking about not hearing? Some people are hearing, some people are not hearing. Is it from your side? If people can hear me, that means it's probably not my side. Some people are talking about the audio, some people are talking about the video. Some people can hear very perfectly. Is it better now? Are you guys good? Okay. Now, I want you guys to have proper understanding of this topic. That's the reason why I'm taking my time on the introductory part. I was trying to explain to you the meaning of all these things so that you guys don't see this as complex expressions in mathematics. This small letter x right here, I told you it represents numerical values. But since we're trying to write a general expression, we cannot be writing probability of x equals to 1 or no. We just put in x there. I told you already, x here is just like a placeholder. It could hold 0, it could hold 1, it could hold several other things. All right. Now, this capital letter x here represents the random variable we're dealing with. Now, what we are saying right here is that the probability of a random variable being equals to any numerical value, if it's a discrete random variable, that probability must be greater than or equals to 0, which I believe every one of you agree with me that generally a probability must not have a value less than 0. That's this first thing you are having here. So the probability of x equals to 0 or x equals to 1 or x equals to 2, depending on whatever experiment we're dealing with, depending on whatever random process we're dealing with, must not be ever equals to minus 0 point something, 0 0.1, 0 0.8. It must never have a negative sign. That's the meaning of this first box. So once you have a situation where you are getting your probability as minus something, that tells you already that that can never be a discrete random variable. So in any case where you discover that there is a possibility or chance for you to say your probability of a random variable happening is equals to a negative answer, just count that out from being a discrete random variable. A discrete random variable says the probability of the random variable being equals to any numerical value must be greater than or equals to 0. So we are okay with it being 0, but we are not okay with it being less than 0. That's the meaning of this very first expression. I'm sure you guys can understand that clearly, but good. Now, let's go on to the second expression. What does this mean? This second expression. I'm sure you guys understand the use of the word summation. This is summation. What we have here is summation. Summation of all the probabilities. The summation of all the probabilities in that random variable. For instance, I will explain this using a dice. The probability of all the probabilities must be equals to 1. If it's less than 1 or greater than 1, it is not going to be a discrete random variable. Let me give you an instance. If you have probability of, if we're dealing with the tossing of a dice or the tossing of a coin, let's use both. Now, let's take our random variable x for a dice as we getting, of course, this random variable x represents the outcome of throwing of a dice. That means we're going to be having it as an element of 1, 2, up till 6. Now, look at this now. The probability of x equals to 1, we know that will be 1 over 6. I'm sure you guys remember all this. Probability of x equals to 2, 1 over 6 also, and so on and so forth. All right. Now, for you to understand this second part, probability of x equals to 1 is 1 over 6. Probability of random variable x being equals to 2 is also 1 over 6. Up until probability of x equals to 6 is also 1 over 6. For you to decide if that whatever you're dealing with is a discrete random variable, the addition of all these probabilities must give you 1. So we go on to say 1 over 6 plus 1 over 6 plus 1 over 6, that's for 3, 1 over 6 for that of 4, plus 1 over 6 for that of 5, plus 1 over 6. If you add all this together, obviously, this should give you the value of 1. And this perfects the fact that this is a discrete random variable. Now, if you do that of a coin, obviously, you have two outcomes. So let's say we're going to define our random variable x as the outcome of tossing a coin. Obviously, it's going to be head or tail, 0 or 1. All right. Now, the probability of x being equals to 0 is 1 over 2. I'm sure you agree with me. The probability of you getting a tail is 1 over 2. And the probability of x being equals to 1 is what? 1 over 2. Now, let's see if tossing of a coin will be a discrete random variable. Let's go on to say the addition of all the probability of the random variables that exceed there, that will be 1 over 2 plus 1 over 2. What does it give me? 1. Obviously, the tossing of a coin is a discrete random variable. Now, if in any case you decide to add up all the probabilities of the random variables, if for any reason you get a value less than 1 or greater than 1 that is not equals to 1, that will not be a discrete random variable. I don't know if you guys can really understand what I'm saying here. Can I get comments from the comment section? Does it make sense? If you're dealing with random, let me recap this, what I just said. Again, you guys don't have to beat yourself too hard. This is the first class. So, of course, I wish to... What is going on with this network? What about now? Is it still blurry? Can you indicate if you can hear me? Is it okay? All right. I think we're going to blame the network for tonight's class. I'll try and do a recap tomorrow when we meet, right? Now, what I said about discrete random variables, I want to recap on it. I said there are two major things that must happen for you to decide that something that you're dealing with is a discrete random variable. Now, I want you guys to understand that in your examination, you could be asked some questions that has to do with you recognizing if something was a discrete random variable or not. If you check your past questions, you will see questions that has to do with something around this particular aspect, where this is the two things they expected you. I think, is it 2 or 3 years ago, they gave a question and they asked you to define that thing they gave you was a discrete random variable. This was what they expected students to do. They expected students to define that for you to have a discrete random variable, two things must happen. Number one, this first thing. Number two, this second thing. Now, what is this first thing? That was what I was trying to say. What is this first thing? Is it one very big expression that looks so? No, it's a very simple thing. Probability of x equals to x. The meaning of this is just saying, I told you already that this capital letter X represents a random variable, and I already explained to you what random variables mean. More like saying probability of, if we're dealing with the tossing of a coin, let's say the outcomes for tossing of a coin is what we define our random variable as. So it's more like we could say probability of you getting a head is 0. That means, of course, this is probability of x equals to 0 means probability of tail, because that means no head. Or we could say probability of x equals to 1. In this case, 1 head. Now, but in this case, when we wanted to define what we are going to define variable on, we cannot be going on to be writing numerical values in this place. That's why we just filled it in with a value, small letter x. This small letter x can take any value, 0, 1, 2, 3, and so on and so forth. It could even take 0 point. depending on, of course, we are dealing with discrete, sorry, so we cannot have 0 point here. All right, but if we're dealing with continuous, there will be a range of values that x can be defined on, which will include decimal. But in discrete, this will obviously all be integers. Now, this x now, instead of us writing numerical values, we just fixed x there because we wanted to define a general expression. We now said the probability of any random variable being anything, we don't matter if it's 0, 1, 2, 3 or anything, it must never be a negative answer. That means we must never have the probability of something being equals to minus 0.3. That's why we said it must be greater than or equals to 0. So if it's equals to 0, we are good. If it's greater than 0, if the answer is 0.25, we are good. That's greater than 0. If the answer was 1.35, of course, this will not happen because this cannot happen. 1.35 will not happen. So it will not, 1.35 will not happen because of the second one. I will explain that second one very soon. But 0.9, 0.85, 0.35, all these values are greater than 0, or even 0 itself is permitted. But less than 0, minus 0.2, not permitted. Once you have a negative answer, we're going to be doing a question very soon where I would hope you guys will be able to remember all these things I'm saying. Once you see that there's a possibility of you getting a negative answer, that will never be a discrete random variable. Now, the point number 2 is that the summation of all the probabilities, when you sum them all up together, your answer must be 1. Guys, I thought we told you already when we were dealing with probabilities that the summation of all your probability must not exceed 1. 1 is the certain, is the whole sample space is embodied around the probability of 1. I thought we said that when we were in class. So these two things are things you already knew, but we're just bringing it to perspective on the basis of discrete random variable. So a probability must not be less than 0, number 1. Number 2, the summation of all your probabilities must be equals to 1. Now, let me give you an instance for this second one. I said, if you were dealing with tossing of a coin, of course, the probability of us seeing a head when we toss a coin, sorry, seeing a tail is 1/2. Probability of us seeing a head is also 1/2. Let's now see. These are the two outcomes, all right? Let's now see what happens. The summation of these two probabilities, what is it? 1/2 plus 1/2 gives me what? 1. That means the tossing of a coin is a discrete random variable. I did that of the tossing of a dice. The tossing of a dice, if we have a random variable representing, of course, the element of a die, the numbers we can get, which is this. Go on to find their respective probability. That means probability of when x was equals to 1, probability of when x was equals to 2, probability of x when x was equals to 3, random variable x being equals to 3, random variable x being equals to 4, 5, and 6. Of course, the probability of x being equals to 1, I'm sure you guys understand this, the probability of x being 1 is actually 1/6. The probability of x being 2 is 1/6. We have done this before. Now, if you go on to add all these probabilities, 1/6 plus 1/6 plus 1/6 plus 1/6, if you had all the 6 different probabilities for each of your random variable, you will still get the value 1. That means the tossing of a dice is equals to 1. The tossing of a dice is a discrete random variable. Now, it's of course common examples, but when you get to some other examples, you may see some examples that the addition may not give you 1. In that case, you have to deny that particular scenario as being a discrete random variable. So these are the two facts you must hold on to. Now, for you to define something as a discrete random variable, it must have its probability. Each of the probability of the random variable must be greater than or equals to 0, and the summation of all the probabilities must equals to 1. That's that for a discrete random variable. It's different from this is not the same thing for that of a continuous, but for a discrete, this is it. So guys, this is where we're going to stop for today. I just needed to introduce this to you. Discrete random variable. Continuous random variable is also quite very similar, but not the same thing. So we just needed to make this, just to recap, for random variables, we said you have dealt with probabilities, So you guys have done several questions on probabilities. I believe there's nobody here that is very that is new to the word probability. Now, instead of us saying probability of us getting a head, probability of us getting a tail, probability of us getting one, probability of us getting a student with an height of 5 point, instead of seeing all those things in a more qualitative way, we can bring it in such a way that we can go on to say probability of a random variable, which we are going to define on the basis of whatever experiment we're dealing with. We said a random variable is a numerical value we assign to the outcome of a random process. So we can attach a numerical value of 0 and say this represents, if random variable x represents the probability of, if random variable x represents you getting a head, that means when I say head, probability of getting a head equals to 0, that means I'm talking about a tail. All right. So this is just the whole concept of random variables. So in tomorrow's class, we'll be going deeper, delving deeper into random variables, where we'll be solving examples, where you'll be seeing how we're going to be using this concept, these two concepts, to solve questions, these two things. And then we'll then go into continuous random variables and then move on to the expectations that has to do with both discrete and continuous random variable. Expectations, variances, those are some of the key things that they do ask lots of questions on. Now, somebody is asking if it's only a dice and coin. I told you that's just because it's easy to relate to those two. There are several other experiments, too many other experiments that we cannot even list them. If we started mentioning experiments from now till the next 2 hours, we will not, even till the next 24 hours, we will not exhaust the possibilities of experiments that can be classified as random variables, discrete random variables. There are several of them. But since you guys are very familiar with dice and coin, we decided to use that to explain. So there are several experiments that replicate random, discrete random variables or random variables. So guys, thank you very much for joining. I hope you enjoy yourself and I wish you all the best. Take care of yourself. Bye-bye.